You know that feeling when you're in an argument and it just feels like you're going in circles? Or maybe you read a sentence that's so twisted and complex, you're not even sure if it makes sense anymore. Well, what if I told you there's a system, a set of tools designed to cut right through all that noise? A way to figure out for sure if something is true, false, or just nonsense. That's exactly what we're going to do. Let's dive into the world of sentential logic.
Okay, so before we go any further, we have to agree on one single non-negotiable rule. It's called the law of the excluded middle, and it's basically the foundation for this whole thing. It's super simple. Every statement is either true or false. That's it. There's no in-between, no kind of true, no maybe. For everything we're about to do, it's black or white. That's the game.
All right, here's how we're going to tackle this. First, we'll meet the 5 basic building blocks, the logical connectives. Then we'll learn how to put them together by building something called a truth table. After that, we'll see how this helps us find statements that are always true or always false. And finally, we'll bring it all back to plain English to see how this stuff can actually make our arguments sharper. Okay, time to get our hands on the tools. I want you to think of these 5 logical connectives as our Lego bricks. Seriously. We start with simple little statements, things like, Phoebe buys a pizza. And we use these connectives to snap them together and build these huge, complex, logical structures. And here they are, the whole crew. You've got not, and, or, the classic if-then, and its cousin, if and only if. Believe it or not, these 5 little symbols are all we're going to need. The cool part is, the truth of any big sentence we make depends completely on 2 things, whether the little pieces are true and which of these connectives we chose to use. So this table right here, this is basically our cheat sheet. It's the instruction manual for our Lego bricks. It shows us exactly how each one works for every single combo of true and false. Look, and is pretty straightforward. It's only true when both P and Q are true. Or is also easy. It's only false when both are false. But that if-then column, that one's a little weird, right? Let's zoom in on that with a real-world example. Okay, imagine I make this deal with you. If you get an A, then I'll give you $1. Now, let's think about this. When did I actually lie? Well, if you get an A and I give you $1, great, I kept my promise. The statement is true. But if you get an A and I don't give you the $1, then I'm a liar. The statement is false. Okay, but here's the tricky part. What if you don't get an A? Does it matter what I do? Nope. Whether I give you $1 or not, I haven't broken my original promise. So in both of those cases, the statement is considered true. And that's the key. An if-then promise is only broken, only false in that one specific situation. All right, so we know the rules for the individual bricks. Now it's time to see what happens when we start building with them. We're going to take a more complex formula and break it down piece by piece. So here's our test subject. I know, it looks a little scary, but don't worry. It just says not P and also if P then Q. See? It's just a mashup of the pieces we already know. We've got a not, an if-then, and an and holding it all together. The trick is just having a system to figure out when this whole big thing is true. And that system is a truth table. It's really just a simple 3-step recipe. Step 1, list out all the possible true/false combos for your basic letters, P and Q. Step 2, work from the inside out. Solve the truth value for the smaller chunks, like the stuff in the parentheses. And finally, step 3, use those answers to solve for the main connective, the big one holding it all together. That's it. And voila, here's the finished table. You can see how we did it. We start with our 4 possibilities for P and Q. Then we made those 2 helper columns for the inside parts, not P and if P then Q. Then for that final column, all we have to do is look at our 2 helper columns and apply the and rule. And since and is only true when both sides are true, you can see our whole formula is only true in those bottom 2 rows. It's totally mechanical, no guesswork involved. Okay, so we can build these tables, but so what? What's the big deal? Well, this is where things get really interesting. We're about to shift from just doing calculations to actually uncovering some deep truths about logic itself. And that brings up a really cool question. Do you think it's possible to build a logical statement that is always true? I mean, no matter what. A statement that's true, whether its little parts are true or false. A statement that is just unshakably true. Well, take a look at this beast. It's a much bigger formula, but we followed the exact same steps, working from the inside out. But just look at that final column. It's all T's, every single one. It doesn't matter what P and Q are, this statement comes out true every single time. This isn't just a statement anymore, it's a fundamental law of logic. And yeah, there's a special name for a formula like that. It's called a tautology. Think of it like a universal truth, a rule of the logical game. And of course, there's an opposite. A formula that's always false, no matter what, is called a contradiction. It's a statement that literally breaks itself. Okay, so this whole always true thing, it unlocks another superpower for us, the idea of logical equivalence. This is wild. It means you can have two statements that look totally different, different symbols, different structure, but they actually mean the exact same thing, logically speaking. Let's take these two for example. On one side, you have if P, then Q. Simple enough. On the other side, you have not P or Q. I mean, they look nothing alike, right? One's an if then, one's an or with a not. But are they the same? There's only one way to find out. We run the numbers, we build the truth table for both. And would you look at that? The final column for if P then Q is identical to the final column for not P or Q. T, F, T, T. They match up perfectly. This is proof. They are logically equivalent, and that is a huge deal because it means we can swap one for the other anytime we want. It's a game-changing shortcut. So let's bring this all back down to earth. All these symbols and tables are cool, but what's the point? How does this help us with, actual English sentences and arguments? Well, this is where the rubber meets the road. All right, take a look at this sentence. If Phoebe buys a pizza, then Calvin buys popcorn. Now let's say I asked you for the negation, the exact logical opposite. Your first gut reaction might be to say, if Phoebe buys a pizza, then Calvin doesn't buy popcorn. Sounds reasonable, right? But it's actually wrong. Our logical toolkit can show us why and give us the real answer. Let's follow the procedure. First, we translate it into symbols. P, arrow C. Simple. Next, we negate the whole thing. Just stick a not out front. Now for the magic trick. We use that equivalence we just found a minute ago. We swap out P arrow C for its identical twin, not P or C. And once we do that, a little bit of simplification gets us all the way down to P and not C. And now we just translate that little formula back into English. The true logical negation is Phoebe buys a pizza and Calvin does not buy popcorn. That's it. That is the one and only situation that breaks the original promise. Our intuition might get it wrong, but the logic led us straight to the precise correct answer. So what are the big takeaways here? First, remember that logic isn't about making things complicated. It's about making them crystal clear. Second, those truth tables, they might look like a bit of work, but they are a foolproof tool for finding the real meaning of a statement. And finally, this isn't just for a philosophy class. This is literally how computer chips think, and it's the foundation for making any argument that actually holds water. And that leaves me with one last question for you. We've seen how these tools can take a messy sentence and make it perfectly clear. So, what do you think would happen if we started applying this kind of thinking not just on a whiteboard, but inside our own heads? If the language of logic can clarify our statements, how much more could it clarify our thinking?